thanks, Dima.
Also, Ben is Jacob's postdoc something. Anyways, it's not so relevant,
right.
but anyways.
Not necessary knowledge for the talk, but still important. Great. Yeah, thanks, Dima, for the introduction. Yeah, I have a talk prepared, but maybe not all the dates on the citations and things. So if there's something wrong with the citation history here, feel free to correct me, but try to be nice about it. No, I was gonna like add the years, you know. Come on, Brent. All right, so I'm going to be speaking on Yeah, exactly. Yeah, this is actually a plus. So I'm going to talk about consequences of the random matrix resolution of the, I'll just abbreviate it PT, Peterson-Thom conjecture. This is joint work with David Jekyll, who's here virtually, you know, up to finite index, and Shri. Yeah, exactly. Who's always here. And so, I will recall the conjecture which was stated in Murray's talk, because unlike Murray's talk, you know, mine is going to be focused on the actual operator algebra's structural implications and not as much on the random matrices. So, you know, she focused, you know, in a nice way on the random matrix part of it, and I will just sort of focus on the operator algebra. So this is was a conjecture, now a theorem. I never know how to address these things. By Peterson-Thom in 2011, which was suppose that I have a diffuse and amenable von Neumann subalgebra of say, interpolated free group factor. If you know what that is, then you know what that is. If not, just think that T is an integer here. And this is the free group factor on T letters. And when I say less than or equal to, I mean that it's a unital von Neumann subalgebra. Okay, it shares the same unit and it's closed in the appropriate topology. So suppose that we have this, then there is a unique maximal amenable P inside of L of Ft. So it's maximal amenable as a subalgebra of L of Ft. Every proper superalgebra of it is not amenable, so that Q is contained in P. Again, some of you have seen this talk or versions of it a bit, so you'll already know the caution I'm going to provide you, but let me nevertheless give it, which is that you know, the existence here is not really an issue. That's more or less Zorn's lemma. It's not maybe trivial from that, but it's a good exercise. But the uniqueness is really the crucial point here, that there's only one. Okay, so a priori, there could be several. Zorn's lemma doesn't give you any kind of uniqueness. And I'll give a different reformulation of this later. I want to sort of briefly mention the history, but there's sort of lots of results in this direction. So I'm just going to throw a bunch of names on the board and not sort of fully explain the results. But Popa in 1983 proved maximal amenability of the generator massa, and this is the first example of a maximal amenable subalgebra of something that wasn't a factor, right? So this is an abelian algebra, but it's still maximal amenable, and up until then, people thought maybe that all maximal amenable things inside factors were also factors. And then there's lots of other results in this direction. Certainly Voiculescu's foundational work, again, I forgot the precise dates, but in the 90s on absence of Cartan is sort of pointing in this direction, as is Go's result on primeness. And then there are lots of others. There's like, this sparked a whole area of research on just sort of figuring out what are examples of maximal amenable subalgebras of, well, things in general, but in particular for free group factors. A lot of these papers are focused on proving that a specific subalgebra of a free group factor is maximal amenable. Okay. I'm going to tell you that this conjecture is true, so all of them. But yes, very good question. But okay, I will actually, in a more serious manner, address this in a bit. In previous work, they sort of investigated, as formulated like this is not something you can test example by example in a very easy manner. But there's a reformulation where you can, and a lot of work was done in that direction. So I'll talk about that in a bit. Yeah, but good question. And so these all sort of, in some sense, motivate this conjecture, but a lot of the motivation came from the Peterson-Thom paper itself, where, okay, they prove this not for the algebra, but for the group. Now, if I say it that way, it's kind of silly. Amenable subalgebras of free group, or amenable subgroups of free groups are just cyclic. And it's not hard from the combinatorics of free groups to sort of figure out that, the only way you can be contained in another cyclic group is one of you to be a power of the other, and et cetera, and work with non-canceling words. But they didn't just prove it for free groups, they proved it for things like hyperbolic groups, or things which are measure equivalent to free groups, if you know what that means, or lots of sort of things that are analytically similar to free groups. And once you have sort of, and they proved it using L2 Betti numbers, which is, okay, if you don't know what that is, that's some analytic tool. So if you have sort of analytic reasons for this fact, you start to expect that you have some shot of proving it on the von Neumann algebraic level, instead of just having this purely algebraic proof of, well, all the amenable subgroups are cyclic, and think about that. So there was a separate reformulation of this conjecture in terms of what's known as the absorbing amenability property. And what it says is, so let me say it like this. So we'll say that a subalgebra of a von Neumann algebra, this is just some von Neumann algebra, has the absorbing amenability property if whenever I take a subalgebra which is diffuse, and let's say this is a finite von Neumann algebra. If you don't know what it is, don't worry about it. But basically, I just want to avoid some potential issues that I don't want to talk about. So if you have a diffuse amenable subalgebra whose intersection with P is diffuse, then it's actually contained in P. I guess I should mention diffuse means no non-zero minimal projections. But in the finite case, you can just think that it means that you have an isomorphic copy of L infinity functions on the unit interval as a subalgebra. Okay, and so what this is saying is that in some sense, if you have large intersection with something amenable, you have to actually contain it. Right? So for instance, on the free groups themselves, if you have a cyclic subgroup which is sort of maximal cyclic, which is not a power of any other word, if it intersects infinitely another cyclic subgroup, it has to actually contain it. And again, Peterson-Thom proved this for other things that are like free groups, like hyperbolic groups and stuff like that. And now, sort of to address George's question, this is something that you can test sort of example by example. You can try to take P to be, say, this generator massa, this L of Z free product 1, inside of L of Z free product Z, and you can try to prove that it has this property, and that this was done. Cyril Houdier proved this, and then this was also proved. This again sparked a lot of research. Again, I'm just going to throw names on the board in the interest of time. But I will say sort of a bit about this. So Ozawa had a paper in this direction. Brotier Wen had a paper in this direction. Boutonnet Houdier had a sort of a very general paper about this absorption for free products. crack schemata when. And then sort of one thing that's important for my talk in a self-serving manner is this paper of myself, David, Brent, and Thomas Sinclair. And so again, I don't want to go into a whole bunch of details in this direction. I'll also mention some work of David just by himself. I don't want to go into a whole bunch of details, but basically what I want to say about sort of the first, I'm not good at combinatorics, so I can't count. But the first, I think, 5? Yeah, 5. Cool, I got it. The first 5 examples is that these are all focused on specific maximal amenable subalgebras, right? So something like the generator massa or the Laplacian massa or something like that, it's just proving that this example has this property. Now, the conjecture itself is equivalent to saying that every maximal amenable subalgebra has this property, right? So there were sort of just entire papers that just proved specific examples, but the conjecture is about all of them, right? It's about all maximal amenable subalgebra. And you know, these proofs that did these specific examples, they used some strengthening of Popa's asymptotic orthogonality property, which is nice, but sort of doesn't give you sort of a path to solving the full conjecture, at least as of yet. I mean, maybe there's some modification, because in order to apply it, you need to know something about the precise structure of the subalgebra. It's hard to do something in this total generality where you don't really know what a maximal amenable subalgebra of the free group factor looks like. And so the significance, I want to say, of these 2 papers is that in this, me and my co-authors give sort of a free probability proof, sort of similar to, you know, in spirit following, you know, Voiculescu's foundational result on absence of cartons. We give a free probability proof based on some random matrix models and concentration of measure that this algebra has this property. And then David, well, it's sort of related, but mostly important work that I want to highlight, that, you know, he proves for a lot of these perturbations in the sense of sort of Q-Gaussians and things like that, of free group factor properties, that actually sort of the massa you would create turns out to be conjugate to the generator massa itself, which is a extremely surprising result. When he told me it, I did not believe it was true, but it's true. And that sort of says that these subalgebras also have this property. Yes. Right. So yeah, it is an open problem. If this is sort of the frustration with this Peterson-Thom problem, which is that it's still an open problem if a maximal, if an abelian subalgebra, which is also maximal amenable in the free group factor, if that's conjugate to the generator massa. Right. It could be true in principle because they're all freely complemented, and then you do this. However, I don't currently see any route to actually proving that. I don't necessarily think that it's true. There's not really much evidence that it's true, other than you can't do it. But you know, I mean, we do. David's work is probably the best evidence that it would be true. But I think trying to extend that to a very general setting is not likely. And you know, it's the same sort of objection you could make about a lot of these absence of Cartan results that show up that say if such and such a thing has positive first Hilbert number, then the generated algebra has no Cartan. I mean, those things could also be free products. So I think that's not even known. Right. So right. So that is certainly a question floating in the background, which I think is an important direction for future research, but is not what this addresses. So as Murray already talked about this morning, I'm not going to restate the whole thing, but there's a theorem of mine that a natural random matrix conjecture on strong convergence implies the Peterson-Thom conjecture. The conjecture is what Murray stated in her talk, either for GUEs or Haar unitaries. And so this was proved in the GUE setting by Blinsky-Capitan. And this April, Bordunov-Collins gave a solution for the Haar unitary case. Each of these papers by themselves are enough to resolve the conjecture. And this they proved on the nose what I asked, and then Bordunov-Collins proved it for Haar unitaries, along with like lots of questions that not only did I not ask, but nobody asked, and are extremely general. So kind of, they have lots of fun statements like they can prove some nice estimate on LP norms when P is the most exponential size of the matrix to some power, whereas for my conjecture, you need this. And this is much bigger than this. So it's rather impressive work. And yeah. Okay. I don't want to say much about this. This has already been sort of mentioned in Murray's talk. I'll mention a few things that sort of what goes into this is essentially sort of a couple of different tools. One is, again, some concentration of measure argument to basically say that, well, I'll get to it in a bit, but behind this, there's this notion of this entropy, this sort of measure of finitary models. And so what you say is that if for a subalgebra, if that's small, then basically when you try to choose models of this subalgebra at random, you can run a concentration of measure argument to say that those models have to be conjugate on this subalgebra with very high probability. And then you run sort of well-known characterizations of non-amenability in terms of getting you a spectral gap set to basically say that that can occur if you have strong convergence. And hiding in the background here is an important C-star algebraic property, which is local reflexivity of, say, the C-star algebra generated by free semicirculars, or the C-star algebra, say, of the free group. Just any sort of free product of the abelian things, which is true because they're exact by work of Dykema, and by work of Kirchberg, exact implies local reflexive. Okay, all right. So let me briefly get into what's under the hood here to some degree. And so I'm going to mention very briefly, I'm not really going to even define it, I'm just going to sort of wave at it and watch it go by. This one-bounded entropy. So you have this, if you have a tracial von Neumann algebra, so that means I have a von Neumann algebra and tau is a faithful normal tracial state. Then there's this quantity which we call the one-bounded entropy, which is either minus infinity or a non-negative real number or plus infinity. And instead of giving you the precise definition, I'm just going to tell you what it does. So I mean, there's one thing I want to mention, which is that it's a modification of Voiculescu's important microstates free entropy dimension. From a series of papers from 94 to 96. And it's implicitly defined in a paper of Kenley Jung. He doesn't actually write down this constant, but I can point you to a specific part of a specific proof of a specific theorem that, if you look at it, tells you this constant is there. And so observing this, I wrote down an explicit definition, and I probably got the publication date wrong. Okay. And so again, without going into technicalities here, it's some sort of measurement of how many finitary models you have. So you look at your matrix algebra, it's generated by some tuple of, say, self-adjoints. You try to find tuples of n by n matrices of self-adjoints which have the same size tuple, and so that traces of polynomials of them sort of approximately match up, and you try to measure how many you have. Yes, that's right. Yeah, there's also, I believe, again, this is done last minute, so I don't have the dates, but Shen and Shen Hadwin, which do, again, more or less computes this, defines the same constant. Okay. And so instead of giving you the definition, mathematicians like to work with axioms. So I'm just going to give you the property. The first one I already mentioned. It's minus infinity or a non-negative real number plus infinity. It's non-negative if and only if m embeds into an ultra power of the hyperfinite to one factor. Okay. Basically, if and only if m has finitary approximations at every level, given some degree of approximation, I can find large enough matrices which satisfy it. It's 0 if, say, m is hyperfinite. And so, right, by Kahn's work, this is equivalent to being amenable. We're at the Fields Institute, so I have to mention the Fields winning work of Kahn. It's plus infinity for all the interpolated free group factors with index bigger than 1. Or just more generally, if I can generate by x by some tuple of, say, self-adjoints, whose microstate's free in 3 dimensions bigger than 1. It's subadditive under joins with diffuse intersection. It's not subadditive under joins in general. Otherwise, it would be 0 for every finite free product of abelian things, and it's not 0 for L of F2. If they're diffuse. So this by definition is the von Neumann algebra generated by the union. Okay, and so the point is if somehow you have large intersection between these two subalgebras and you're trying to find finitary models of both of them together, you're sort of constrained by forcing them to sort of agree on this large piece, and that gives you enough information to get this estimate. And one thing that I'm going to immediately generalize, I'll list a few more, and then give some exercises. Is that if I take the normalizer of a diffuse subalgebra, so this is the unitary normalizer, then the entropy doesn't increase when I take the normalizer of anything diffuse. And there's one last property which, okay, if you don't know about ultra powers, just safely ignore this. If you do, maybe think about this for a bit. If if m is inside n is at most m omega, then h of m is at most h of n. Okay. So here I'm embedding m into m omega diagonally. Okay. So for example, just from these axioms themselves, you can immediately prove that any free group factor or interpolated free group factor does not have any Cartan subalgebra. In fact, does not have any diffuse regular hyperfinite subalgebra. Right? Because regular means that the von Neumann algebra of the normalizer is the whole thing. If that were to happen, the entropy of the free group factor would be at most the entropy of the hyperfinite thing, which is 0, but the entropy of the free group factor is plus infinity. By a slightly more complicated argument, you can recover Gauss result on primeness of free group factors. You can prove that anything for which this is positive cannot be generated is prime. So to say it in a slightly simpler term, cannot be generated by two commuting diffuse subalgebras. You can also prove from these properties, particularly using the last one, that it has to have property gamma if it's a factor, say. So meaning that it doesn't have, basically the central sequence is that the commuton of m inside m omega is not diffuse. Okay, so those are all exercises. Right, and so that's sort of the point of these axiomatic properties. It turns, once you establish these, it turns some of these important theorems into sort of exercises from the axioms. Okay. And before I get to sort of fun time mentioning applications, I should just mention sort of what goes in between the random matrix conjecture and the Peterson-Thom conjecture. Which is the following. This random matrix conjecture that Maria talked about implies that the statement that if I take if I take a subalgebra of a Frege factor, then the statement that it has entropy 0 is equivalent to the statement that it's amenable. So in other words, establishing this random matrix conjecture, which is proved now by Scherbon and Murray, as well as Charles and Benoit, establishes that whenever you take a subalgebra with entropy 0, it has to be amenable. Okay. Now, this immediately implies this absorbing amenability property, because if I take something which has diffuse intersection with it, right, then if I look at their join, that has entropy 0 by this condition, right, if they're both amenable. And so because of that, their join has to also have entropy 0, has to therefore also be amenable, and then my maximality has to be contained in the maximal thing. So establishing this, easily proves the Peterson-Thom conjecture. And this hard work I mentioned about like concentration of measure and local reflexivity and this Kohn-Hagerup characterization of amenability goes into sort of this implication. Okay. Great. Sorry, Dima, do we go for 50 minutes or 1 hour? Right, but do I have 50 minutes or do I have an hour? All right, we'll keep it to 50 minutes then. Okay, good. Let's not test people's stomachs. That's a bad strategy. Otherwise, I might be lunch. Okay. So the first thing that I want to discuss here is some sort of generalization of this. So this requires some C-star algebra background. So if I have a C-star algebra, let's say unidal, because I just don't want to make mistakes. And I have two unidal star representations. Okay, of this C-star algebra. Then I say that they're disjoint if the space of bounded linear A-modular maps from H1 to H2 is 0. So basically, if I take a linear map from H1 to H2, which is continuous and A equivariant, then it has to be 0. Okay. So if this is completely obtuse to you, here's a good exercise. I could take this, I could take continuous functions on some compact Hausdorff space, and I could take some nice, say, Borel probability measure on that space, and I could define the multiplication representation. And then these being disjoint for two measures mu and nu is the same as the measures being singular. So this is like a non-commutative harmonic analysis notion. It's some way of sort of abstracting singularity of measures to just algebras where you don't have measures. Yes, I believe that's equivalent to what I stated. Yeah. So yeah, a linear bounded maps, alinear continuous maps. Yeah, those are, is that what they call intertwiners? I think so. Okay. And so I'll use this to define, given an inclusion n inside M of subalgebras, I'll use this to define what is now called the anti-course space. So I look at all vectors in L2 of M, and I take the MM bimodule, which will denote L2M psi M generated by psi. So you just multiply on the left and the right by elements of M, and you take linear combinations of those, and you close that in the 2 norm, and that's some MM bimodule inside L2 of M. So I'm going to ask that those are so that bimodule is disjoint from the course bimodule. And disjoint in what sense? I have to produce some C-star algebra as, say, a representation of the max tensor product of these two C-star algebras. Okay. You can actually define this disjointness for just representations of star algebras, but okay, fine. And so to give a bit of intuition as to how, to sort of why you would consider this, it's sort of a chain. You have to compose analogies, essentially. So in sort of the Kahn sort of correspondences picture, you're supposed to think of bimodules over von Neumann algebra as analogous to representations of groups. Under that analogy, the course bimodule corresponds to sort of the left regular representation of the group. If the group were abelian, the left regular representation of the group, representations of the group correspond to measures on the dual, and the left regular representation corresponds to the Haar measure. Right? So this is some sort of singularity with respect to some non-commutative Haar measure, and that's why you consider it. And so sort of another thing that's important here is that this space contains the normalizer. But it, oh, n, yeah, you're right. Yeah, I want the NN bimodule. Yeah, you're right. Yeah. All the m's should be n's. Yeah, my bad. Thanks. Right. So okay, now this proposition is true. Okay. But it also contains various other things. And so, what happens in von Neumann algebras in sort of considerations like cohomology theory or subfactor theory or things like this is lots of other sort of wacky normalizers pop out. So this wacky normalizer is the unitaries in M, so that UN U star intersected with n is diffuse. And so now sort of in this picture that we're thinking of just sort of considering things up to sort of having large intersection, I'm now not saying that this conjugate is equal, but that they see a lot of each other. Okay, and there's a natural group theoretic analog of this. You consider conjugates of a subgroup whose intersection with the subgroup is infinite. And this one-sided quasi-normalizer would be the set of x and m, so that there exists x1 to xk in M, with xm contained in the sum of mxj. Okay. And so, right. So the point of this is that, okay, if you had a genuine normalizer, you could do this with k equals 1. It would just mean that, oh, this is n. Sorry. Why do I keep doing that? Great. It would mean you could do this with k equals 1. A normalizer would be un is nu, right? but now you allow yourself some summation. And so like a different way to say this is that the NN bimodule this generates is finitely generated as a right n module. What? Yeah, it's x and m. So there exist some things in M, so that x, n, this, okay. And so this says, for instance, that the NN bimodule generated by x is finally generated as a left n module. Okay. Which is actually some, there's some various ways to think about this. This is kind of, again, if you think of bimodules as analogous to group representations, it's like saying you have a compact representation of a group. And again, if you did this for inclusions of groups, this would boil down to what's known as the one-sided commensurator, which is, again, an important thing in geometric group theory. Okay, let me not get into that. So in the remaining, I guess, 15 minutes that I have, I want to, again, talk about more applications. And so the sort of, I would say, actually, the significance, I would say, of this paper where I sort of write down the definition of the one-bounded entropy is not, to me at least, is not actually the definition. Indeed, it was sort of already implicitly in like 3 other papers. It's the following theorem, which is that if I amp up, so if I take an inclusion of algebras n inside M, and I look at some subset of the singular subspace. Now in my paper, this can really be any subset. It doesn't have to consist of bounded things. But just to sort of make life easy, let's intersect with the bounded elements. Then the entropy of the algebra that generates is at most the entropy of M. Okay. And so for instance, you automatically get the result for the normalizer, but you also get it for this WQ normalizer and this one-sided quasi-normalizer. And let me sort of more or less promise you any kind of normalizer you would actually write down. And also because of these abstract properties, you can also just immediately do it in an ultra power if you want. Why not? Okay. And I should mention that for the case of the normalizer where the subalgebra is abelian, this is actually essentially just Wojciechowski's proof of absence of Cartan subalgebras. He didn't write it in this way, but basically, he more or less just directly used disjointness of 2 different bimodules to analyze things, but in the special case where one of them is abelian, and so you can actually write down measures and things. And so this led me to the following conjecture in the same paper. Actually, I really think it was 17. Which is if I have a diffuse and amenable subalgebra of a free group factor, of interpolated free group factor, then when I look at the orthocomplement bimodule as an NN bimodule, this embeds into an infinite direct sum of the course. Okay. And one immediate corollary of that theorem and the this intermediate theorem that entropy 0 means amenable in a free group factor, you get that if this is true. Great. Okay. Let me sort of mention a special case of this. You could imagine the case where n is abelian. Let's call it A. Right? So now we have an abelian subalgebra, which is also maximal amenable. And then what I can do is I can say that A is, say, some L infinity of x mu. And I can consider the representation I get of C of x times x on bounded operators of L2 of M intersect L2 of A orthogonal complement I get by, again, just sort of left and right multiplying. So here I'm just literally thinking that A is L infinity of X. And while this is a representation of some continuous functions on some compact Hausdorff space, so it corresponds to some measure, right? That's what we learn in the spectral theorem. So this gives us a measure on X times X. And the rephrasing of this conjecture is that this measure is always absolutely continuous with respect to the product measure. Okay, so in the case of abelian things, this analogy with singularity is not purely an analogy. It has an actual explicit corollary. And this was done by sort of previous work in this direction. It's basically folklore for the generator massa. We can probably just attribute that to Voiculescu. But sort of some work in this direction was done by Dijkema and Merkur-G, 2012. Radulescu, I think, had this for the Laplacian massa. It is sort of strongly used in a paper of Dima and Cyril in 2011, and also in one of these other papers I mentioned before. Okay. Yeah, sorry, diffuse and maximal maintenance. Yeah, thanks. Yeah, otherwise it's not true. Right, yeah. Otherwise it's definitely not true, yeah. Great. Okay. And of course, if you're fun and wacky, which we like to be sometimes, we have fun sometimes, then you can do this, you can do this in an ultra power with no problem. Why be serious when you can be fun? Right. I choose an idempotent ultrafilter, so it's fun. I don't know. I could take some finite list of things where Qj is say Q1 is diffuse and amenable, and each Qj plus 1 is generated by Qj and some Xj, where Xj is inside the singular subspace of Qj inside Qj plus 1, or sorry, inside M omega. And okay, as written, K is a finite number, but it could be an ordinal, if you know what that means. Then whenever I intersect this with the diagonal copy of M, this is always amenable. So for instance, it implies this gamma stability that, like, if you have a diffuse subalgebra of a free group factor whose central sequences inside the free group factor are diffuse, then actually that subalgebra is amenable, et cetera. Great. We also get, so if I did this without the omega, this is by itself already a generalization of strong solidity. So let's call it mega solidity. So the generalization of the strong solidity theorem. With the omega, it's ultra solidity. Without the omega, it's just, I can do all sorts of weird normalizers, and so what Ozawa and Popo proved is that if you take an amenable thing and you take the von Neumann algebra generated by its normalizer, then it stays amenable. But now I can do this with all these other wacky normalizers. So it's mega solidity, but I can do it in M omega, so this is omega mega solidity. Okay. I told you we would have fun. Okay. Let's see. Does that include 5 minutes with questions or without? Okay. All right. I want to mention just one last application. Again, there's lots you can actually do with this. We're already sort of starting other projects where we have lots of applications. Shri has a nice paper with Greg Pacho that talks about sequential commutation of unitaries inside an ultrapower, and he gets lots of nice applications for free group factors from this. I think this is maybe going to hit a sort of small subset of the audience, but I do want to say something about the relevance of this for this deformation rigidity program. So I'll say that Q intertwines into P if I have subalgebra of M, if there's sort of projections in Q, projections in P, and a unital star homomorphism from these corners, and some V in M, so that XV is V theta X for all X in FQF. VV star is an FQF prime intersect FMF. And V star V is in theta FQF prime intersect EME. And I guess this should be a partial isometry. Admittedly, this is a sort of bit to parse if this is your first time seeing it, or even if not your first time seeing it and you just don't work with this that often. But you should sort of imagine the situation where F and E, this should be not zero. You should imagine the situation where these non-zero projections are just 1 and that V is a unitary. In which case, you're saying that basically these subalgebras are unitarily conjugate. But this notion is slightly more flexible. You can not just have unitary conjugacy. You can take sort of corners of things and have those be unitarily conjugate, et cetera. And in fact, often the way you get that things are unitarily conjugate is to start from this and then sort of start patching things together. And so what we get from this is this dichotomy for maximal amenable subalgebras of free group factors. Which is that if I take two subalgebras of a free group factor, which are maximal amenable, then exactly one of the following occurs. So it's a strict dichotomy. Either there are non-zero projections in P and Q, and some unitary in M. M is my free group factor. So that these corners are conjugate. So either they have unitarily conjugate corners, or for every diffuse subalgebra of Q, I cannot intertwine it into P. Okay? So either they don't see each other at all, right? Anytime I take any sort of large piece of it, I can't move it into the other whatsoever. Or in fact, up to cutting by corners, they're actually unitary conjugate. For instance, if Q and P are subfactors, the first item automatically implies that they are conjugate. If they're not subfactors, then we sort of investigate this analysis more. I guess, in short, you might wonder whether the resolution of the Peterson-Thom conjecture, solves the problem but is otherwise useless. Maybe it doesn't get you closer to solving the free group factor problem or something. But as we've shown, and as is sort of further work we're developing, that's not the case. We get lots of interesting applications to the structure of free group factors beyond just solving the Peterson-Thom conjecture. I'll stop here so that you can eat.